Hello and welcome to this short clip on how to write electron configurations at A-level chemistry. So you need to make sure that you're completely comfortable with the order in which orbitals are actually filled. So on any one energy level, 1, 2, 3 or 4 for example, the electrons with the lowest energy fill their orbitals first. So that gives us S, P, D and then F. So let's look closely at 1s, 2s and 2p. We start with 1s1. So if we have one electron in the 1s orbital, we get 1s1. If we add another electron, that now becomes 1s2. Add another gives us 2s1, and as you'd expect, 2s2. So when you get to 2p, what you find is that the electrons don't really want to sit next to each other because they repel. So this means that you actually now have space for them to actually sit further apart. So this would be considered 2p3, 2p4, as you'd expect here, 2p6. So once 2p6 is filled, you can go on to the third energy level now. So we've filled energy level 1, energy level 2. So if you link it back to GCSE, you now have 2 and then 8. So we can repeat the process in energy level 3. This now gives us a further 8 electrons. But you'll notice that we haven't started filling the 3D yet. So taking that into account, the actual energy level 3 is not full until we have the 3D subshell filled as well, which gives us 3D10, which actually means we now have 18 electrons in the third energy level. If we look at the first 10 elements, you can see clearly there's a pattern that gets followed. And a good way to check whether you're on the right track is to count up all the electrons, and they should equal the proton number of the atom printed in its box in the periodic table. So why don't you grab your periodic table and have a look. And you should also find as a quick check, if you need to, that these actually match the GCSE electron configurations that you would have applied to them, like so. So there are checks and balances you can use to make sure that you're doing it right. So in the periodic table, we classify elements according to what block they're in as well. So the S block, for example, has the orbitals, the s orbitals being filled. The D block has the d orbitals being filled. The P block has the p orbitals being filled, and the F block has the f orbitals being filled. So the orbital where the highest energy electron is entering is used to decide that element's block. So if you look at all the rows and all the sections, that particular orbital, it'll be a 4d orbital, for example. Here, all the elements in that row will have a 4d orbital being filled as the highest energy electron. All these ones will have a 5p orbital being filled by the highest energy electron, and so on and so forth. So if we look at the oxygen atom, it's currently filling the 2p orbital with its highest energy electron. So it's in the p block. So here are 4 examples: boron, carbon, nitrogen and oxygen. There's 2 things you can get from this. First of all, they're all in the p block, and secondly, they're all filling the 2p orbital, or should I say the 2p subshell. And if you check your periodic table, you can see the area where they're all found. So it's no coincidence. The periodic table does actually go with the orbital model of electron configuration. So the highest energy electron is filling orbitals in the 2p subshell in each case. These have been highlighted in green on the diagram so you can see the highest energy electron. It should now be pretty obvious that if we look at the halogens, they're all in the p block. And that's because their p orbitals are being filled, which I've now highlighted. So to reiterate, an element's block is always based on which orbital the highest energy electron is filling. So these examples just include the 4s and the 3d subshell to show that the order of filling. There are two slight anomalies, chromium and copper. So first looking at chromium. What chromium does is it moves one of its 4s electrons into an empty space in the 3d subshell. So now what you have is you've actually got 6 electrons that are not paired up with any other electrons, so therefore what they're not subject to is repulsion. If an electron pair in an orbital is subject to repulsion, then it's possible that another atom nearby might want to take one of those electrons. The ones that are vulnerable are the 4s electrons because they're of lower energy in that particular energy level. So 4s and 3d sit in energy level 3. And what happens is that the 4s electrons are vulnerable to being removed or ionized. So when an electron is removed, this is called ionization. So it's a similar situation with copper. It's more stable for the atom if there's one unpaired 4s electron, so the other one is moved into a 3d subshell. So it's given a small boost of energy by the atom to do this, just like what happened in chromium. So although we've looked at energy levels 1, 2 and 3 in detail, exactly the same idea applies to energy levels 4, 5, 6 and beyond. So the principle is the same. The s orbitals fill first, then the p orbitals, then the d orbitals, and then the f orbitals. So hopefully this has been a reasonably useful introduction to how we actually write electron configurations. If you have any questions or queries, why not write them down and bring them to one of us at college, have a chat to someone in your subject extension, or perhaps go and see a teacher. In the meantime, thanks for listening, and see you soon. So when it comes to the transition elements, it shouldn't be difficult to work out that they're actually in the D block if we use their electron configurations. I just want to make a mention of when it says noble gas configuration. So noble gas configurations are sometimes used as shorthand. So for example, if you take square brackets and put AR in them, all that really means is that before you get to 4s, as in the electron configuration that I've given, all the other orbitals in lower energy subshells, namely 1s, 2s, 2p, 3s, and 3p have been filled already. So because 1s2, 2s2, 2p6, 3s2, 3p6 is the same as the argon atom, we put the argon symbol in square brackets. So although these shorthand versions are technically legitimate, it's a good idea to try and stick to full electron configurations at A level and not get into shortcuts like this. So if you were to look on the open internet, for example, you may well see this kind of shorthand being used. I just wanted to make a mention of it so you know what it means. So if you were to have an electron configuration with neon's electron configuration within it somewhere, so it would begin with 1s2, 2s2, 2p6, you could put in square brackets Ne, or for 1s2 you could put He, but like I've said, try to stick to the full electron configurations of your elements at A level if you can. Don't fall into the habit of trying to find shortcuts. So let's now try some examples and practice examples from past examinations. What you might want to do is pause the video, keep this screen up, grab a piece of paper and have a go at some of these. So you'll see that in some cases they've given you the beginning part of it, maybe more than just 1s2, they might give you quite a lot. So based on the previous slide, you can probably clearly see that this one here would be argon. So the first one is carbon. We've looked at carbon in this clip already. What I suggest you do is make sure that you've got your periodic table handy and you can practice it using your periodic table. So the next one is bromine. And I just wanted to make an interesting note about 4s2 and 3d10. In electron configurations you can write these either way around. That's actually allowed in the examination. What I've done here is, because 4s2 fills first, I've put that in before 3d10, but the actual energy difference between them is quite small, as we talked about at the beginning of this clip. So if you wanted to put 3d10 and then 4s2, that's okay as well. But it must be 4p5. So for titanium, that's the 1s2, 2s2, 2p6, then 3s2, 3p6, 3d2, 4s2. And 3d2, 4s2 could be written as 4s2, 3d2. It doesn't really matter which way round they're written, like we just said. Now the next one is interesting, because if you look closely, you'll see that it's got the Cl- ion, not the chlorine atom. So a Cl- ion is a chlorine atom that's gained an electron. So it's negatively charged by 1. So what you do in this instance is you add 1 electron onto the electron configuration for a chlorine atom. So although halogen atoms would end in p5, halide ions would end in p6 because they've gained that 8th electron in their outer shell. So this time it would be 1s2, 2s2, 2p6, 3s2 and 3p6. So let's bring the page down and have a look at the answers. Well, I think we got them all. 1s2, 2s2, 2p2. And we said 3d10, 4s2, 4p5. We did this one, and they allow it. And we did 3d2, 4s2. Just because they didn't say allow 4s2, 3d2 doesn't mean they wouldn't let it pass. So that was fine. And we made sure that we had 3p6, not 3p5, in our final answer there. So hopefully you found this clip reasonably useful as an introduction to doing electron configurations. If you've got any queries, obviously have a chat to your teacher at college, or maybe come and see one of us in a subject extension. But for now, thanks for your time and see you soon.